Part of the lecture is going to be remote, like by our guest speakers, and like then we will get back to in-class lecture. Okay, so as I mentioned last week, for the first couple of sessions of this lecture, like so we have an invited guest lecture, like by Harm was saying, like Harm is the lead of the reinforcement learning research team at Microsoft Research Montreal. So Harm works in several fundamental problems in reinforcement learning. Like so, today he's going to teach us about eligibility traces. Like so, one of the main reasons why I invited Harm to give this lecture is like so he was also involved in development of some of the algorithms that we are going to learn today. So. And Harm is also one of my team's, like, I can't say long term because we are only 2 years old, but like for a long time, like so we are collaborating on a lot of multiple projects, and like he's also a really great speaker. So I'm very much excited to see what he teaches us today. So thank you for accepting this, Harm. Like so you can share your screen and get started.
Yeah. Thanks a lot for the invite. And yeah, sorry that I'm not there in person. I'm in Montreal. I live in Montreal. I just, as you may hear, I have a bit of a cold, and I didn't want to risk infecting you guys, especially not with current COVID anxiety. So I just decided to do it remotely from my own home. So apologies for that. Yeah, to give some further context to what Sarath was saying, I did my PhD a long time ago at the University of Amsterdam, working on reinforcement learning. After that, I did a postdoc with Rich Sutton at the University of Alberta, and there I worked, among others, on eligibility traces. Eligibility traces has been around for a long time, so you may think, is there still something to improve there? But as it turns out, there was, and there was something behind underlying theory that wasn't completely correct. So that's something that I worked on, and it actually led to an improved version of eligibility traces. So I'm going to talk. I'm very happy to talk about that. Yeah, what else? So just to give some further context on eligibility traces. So it's very closely related to multi-step updates. In fact, it's a different way of implementing multi-step updates. So yeah, a lot of the motivations for why you want to do eligibility traces, it's the same reasons of why you want to do multi-step updates. So let me just share my screen, or just create a whiteboard so I have something to work with. Just want to try the interactive aspect of this. I hope I'm still be able to get some question answers going, even though I'm remote doing this presentation. So perhaps, yeah, so can somebody explain why you would want to do multi-step updates instead of one-step updates? Like what's the advantage of multi-step updates over one-step updates? Does anyone have an answer to that?
Well, I think people in the Zoom can unmute yourself and answer, but I will also check the chat. But you can also answer here. I will try to relate. Sorry, can you please repeat it? Okay, so Harm, I don't know if you heard this answer, but to see a little bit more in the future, to see what are the effects of the action.
So what are the effects? So Yeah, so in what cases does that give an advantage? Like, why would that, like, what's the ultimate performance metric that you hope to improve?
Okay, there is an answer in the chat which says you can save computation time.
Computation time? Yeah, I would say that's close. That's not necessarily the main objective. The main objective, I would say, is sample efficiency. So if you have sort of a performance curve where you have the samples on the x-axis, and this is sort of the return on the y-axis. Basically, what you try to do, you have a curve over here. This is sort of what you want to achieve. So you want to get that, go from the blue curve to the red curve. So have a higher sample efficiency. And it's related to computational efficiency as well, but it's not a one-on-one. These are actually two different metrics that you could care about, because you know, it can be the case, like eligibility traces, it will be computationally a little bit more expensive than just something like doing a one-step updates. So per sample, it's more expensive, but you know, it costs you less samples. So in terms of total computation time, you know, depending how that trade-off exactly happens, it can be a little bit more, it can be a little bit less. But the main metric you're optimizing for is the sample efficiency, because samples in practice, those are the most expensive, especially if you're working with a real world task. You know, samples can be very expensive to obtain. The other thing I should mention here, and this is a little bit more sort of history context, like eligibility traces were developed before the whole deep RL revolution. So it were developed initially in the context of tabular reinforcement learning. Also for linear reinforcement learning, it worked very effectively. So in those settings, like these algorithms there, they converge just to the optimal policy. So they behave nicely, converge to the optimal policy. So the main goal then, when doing research on reinforcement back, you know, 20 years ago, was how can we improve sample efficiency? Because you already know it's going to converge in the end, so that was not a concern. So the main target there is like, how can we do it as efficiently as possible? And eligibility traces is a very effective way to achieve that. You know, computation efficiency is also important. So eligibility traces is still a very efficient, computationally efficient method as well. But the main one is the sample efficiency. And so it's sort of yeah, good to realize this, that you know, if you look at papers now, sort of in the deep RL setting, there's a lot of focus on what's the performance, and by which this mean people talk about what's the final performance. And this is because algorithms don't typically converge to the optimal policy. There's all kinds of instability. So the focus is really what's the final performance. But that's sort of a shift that happened in recent years due to deep RL. Like before that, it was really, you know, even like in the tabular case, you just have convergence proof. In the linear case, those convergence proofs are not necessarily there, but in practice, things still behave very nicely. So your algorithms typically converge to something that is close to the optimal policy. And so the focus was really on improving sample efficiency. So, you know, especially in the tabular and the linear setting, eligibility traces played a very important role, like an algorithm like Sarath Lambda that was one of the main go-to algorithms, say 10 years ago. Now, you don't see it as much in deep RL anymore, and we're going to talk a little bit about why that is the case. I mean, you still see multi-step updates, like a simple version of that, but it's not so dominant as it was, as it is for linear and tabular case. And it has to do with certain challenges in combining it with some of the other approaches that are used in DeepRL. And I'm going to talk about that later as well. But yeah, so the general setting here is we have algorithms, they converge nicely. How can we make them more sample efficient? So I want to talk on a high level a little bit about what is the underlying reason, what's the underlying technique that is used to make them more sample efficient. And yeah, maybe that's a good question to ask as well. Like, can anybody, because this I just talked about, okay, on a very high level, what is it that we're trying to achieve? Trying to achieve higher sample efficiency, but what's the underlying reason that we can be more sample efficient with a multi-step method compared to a one-step method? And I think in the chat I saw somebody alluding to that already. Something popped up in my screen. Can somebody give an answer to that? Like, what's the underlying reason that we can be more sample efficient?
Well, I think people in the Zoom, you can unmute and give your answer.
Hello.
Yes, hello.
Yeah, I'm just repeating what I said in the chat, but to lower the bias.
So two questions. So you're saying that with a multi-step update, you have lower bias. That's indeed correct. But yeah, yeah, no, I guess that's a good answer. That's a good answer. So what's the advantage of a lower bias?
The learning is more stable.
Yeah. It's more stable. It can be more stable. Like, I guess the other question is, why not always use multi-step update? Because if it's more stable, shouldn't we always use sort of, let's say, a Monte Carlo update, which is sort of a very long multi-step update? Like, is that always better than a one-step update, or?
Well, it's a trade-off between the variance and the bias, from what I understand. So you want to achieve like the optimal combination of the two. That's why you use n step, because it's between Monte Carlo and ED0.
Yeah, that's a great answer. That's indeed correct. And so let me repeat that and clarify that a bit more. So yeah, it has to do with trade-off between bias and variance, and that trade-off is problem specific. So that's why you can't just have one algorithm that is optimal for all problems. So you can't always use a one-step method or always use a Monte Carlo method, which is the other extreme. It's going to depend on the problem. So on some problems, actually a one-step method is the better choice. On some other problems, it's a Monte Carlo update. And in some problems, it's something in between. So that's the other aspect. Like, if you want to get the best out of your method, of a multi-step method, you have to sort of per problem tune the value of n. And that's the same case with eligibility traces. Like, there is this hyperparameter lambda that you want to tune per problem to get the best out of your method. So I just want to show you true extremes, like two problems where one problem where a one-step method is better, and one problem where sort of a multi-step method is better. So I'm going to start with sort of drawing a very simple problem. Say we have 5 states, and then we have a terminal state. And we're just doing a prediction, so no control. So just a prediction problem. It's a deterministic problem. Say there is +1 on the last transition, and all the other ones are the reward is 0. Now, and say my initial values are of the states are all 0. So the question now is, and let's just say for ease of computation, my gamma is 1. So, you can now immediately see what the optimal value of all these different states is, which is it's 1 for all the states, right? So the optimal value of all the states is 1. And so the question now is, if we now compare a one-step update with Monte Carlo update, which uses the full return, which is more efficient. So here, if you would do a one-step update, so let's see, let's use this one. So I start, this is my initial state, and I go to this state, and at this time step, I update the value of the state, but all my rewards and values are 0. So the update is trivial and just results still in the value of 0. So no change. Same here, same here, same here, same here, until I reach sort of the terminal state. I observe my reward of 1, and then I do an update, and this changes the value of, this changes my value. Let's just try this. This changes my value to 1. So after a full episode, I've only updated the value of 1 state. Now, during my second episode, again, a lot of trivial updates happen that don't change the value until sort of I reach the state just before the terminal state. From then an update, then this one becomes 1. And so this continues. So each episode, my value, 1 more state gets updated. So in this case, it takes like 5 full episodes with a one-step method before all my values are correct. But this is sort of a very inefficient way of doing this in this particular example, because it's just a deterministic environment, right? So in other words, the value of a state, like the definition of a value of a state, is just the expected return. So you get this, given that S is ST. And so because this is deterministic, the expectation falls away, and it's just my like a single return example gives me the exact value. So after a single episode, I know, like, I have all the information that I need to compute the optimal value of each state. And this is what you obtain with a Monte Carlo update. Like with the Monte Carlo update, you use the full return as the update target. And in this particular case, after a single update of Monte Carlo, you get the correct value. So this is an example of a task where Monte Carlo update is actually much better. Why can't we make a Monte Carlo update after making single updates? Well, so a single update, is like a Monte Carlo update does single update. So, but a one-step update, you can't do it, like you can't do a Monte Carlo update after only 1 step. So you can't, at this point, at this time step, you can't do a Monte Carlo update of this state, because the Monte Carlo update involves the rewards, the full return. So you haven't observed all those rewards yet. So only at the end of the episode, you observed all those rewards. It's only when you're at the terminal state, you can do a Monte Carlo update of all the previous state. So what happens with the Monte Carlo algorithm is you sort of, during the episode, no updates occur. You're just sort of maintaining your statistics, storing those rewards you observe. And then at the end of the episode, you're computing the full return for each of these states. And then you do a single update of this one, then a single update of this one, single update of this one, and so on. And so, yeah, so this is an example where Monte Carlo algorithm is actually best. So now let's look at an example where a one-step update is actually the best approach. So let's draw a different one, And I'm again going to use just 5 states to keep it simple. So now suppose we have, this is our task. This is again the terminal state. All these 4 states go here. And let's just say, like, the reward on this transition is all 0. The reward in this transition is, in expectation, it's 1, but it's a stochastic reward. So it's, you know, let's say it's drawn uniformly between 0 and 2 with an expected average value of 1. So in this case, my initial value is, I draw my initial value, initial state is drawn uniformly from any of these 4 states. And I again assume the initial value is 0 of all my states. So in this case, because I have a stochastic reward, I need to average over multiple episodes, multiple observed returns. So in the case of Monte Carlo update, only a quarter of my episodes start. Say I want to know the value for this state over here. Only a quarter of my episode will start from this episode. So and when this happens, sort of, I'm observing this full return. And so for every episode that starts from this state, I'm just averaging those returns. But if I would, I could do this more efficiently by sort of, because I'm absorbing much more of those rewards, because every episode they start goes through this state, and I'm observing again the stochastic reward. So if I would do a 1-step update in this case, and I would, on every episode, I would sort of average over my rewards, get a good estimate for this state over here. And then if I just bootstrap from this one, it's going to be much more effective, because now I'm sort of using every episode to average over my stochastic reward. And sort of by bootstrapping from the value, I get a much more effective method, and it will more quickly converge. So in this example, it's actually a 1-step update that's going to be more efficient than a Monte Carlo update. So this shows that it's a problem dependent, like this bias variance trade-off. It's a problem dependent aspect, and you need to tune it for each problem to get the maximum value. Now, so some general rule of thumbs that you can already observe from just these 2 examples, that is, if there is stochasticity in your domain, then the optimal value, if you do sort of n-step updates, you want to have a smaller n, because there's a lot of variance in the environment already. And if you use a very high n, like there is even more variance introduced in your update target. And so that typically doesn't work well. So if you have a very stochastic environment, you typically want to be closer to something like a 1-step update target. Whereas if you have a deterministic environment, you typically want to use a value of n that is much higher. Yeah, so that's the general, just on a high level, where the performance advantage of sort of eligibility traces and multi-step updates come from. And it has to do with the bias variance trade-off indeed of your update target, which is sort of has a unique, which is different for each problem that you're considering. And you typically don't know the problem that you're facing, right? It's sort of, the dynamics is uncertain. So we have to tune it in advance. Okay, so what's the, before sort of going into more detail about what exactly eligibility traces does. So it, like I said, it's a form of multi-step updates, but it's doesn't, they consider more complex update targets than the simple ones that you have seen up to now. So I want to sort of talk about that a little bit, and more particularly, I'm going to talk about the Lambda-return, which you write like this. So the Lambda-return is, well, I guess the more fundamental question to ask first is, what is a valid update target? Because clearly we have the one-step update target that is often used. This is just this one. So this is a valid update target, and by valid I mean it leads you to convergence. But also, and we've seen sort of the n-step update target, which is, well, this is this one. So we have the n-step update target, but why can't I, for example, I mean, it's just an estimate, right? So why is do I need this part? Could I just leave the bootstrapping out? Would that still be a valid update target? Like, could I just, how about I define a new update target and say, well, you know, how about I'm just going to look at the first two rewards? Could I use, I mean, I could use that as an update target. I can, you know, construct an algorithm that sort of uses that, but, you know, it wouldn't converge. And so there is the question, like, what's a valid update target and what's not a valid update target? So clearly, you know, this one is not a valid update target, whereas these are okay. And so, like, ultimately, this has to do with the contraction property, so that if you perform updates with an n-step update target or a one-step update target, then, and if you do that for all states, then you know that the error is gonna, on average, gonna reduce. And this holds for these two, but not for D. And the underlying reason is that, or sort of a, yeah, like the true reason is that the contraction property should hold, which doesn't hold for this last one that I drew. Like one way to sort of a rule of thumb to view whether something is a valid update target or not. So if you look at the one-step update target, so you have this v value here, which is just an you know, it's an estimate of a value. So the whole update target by itself, it's not you know, it's a biased estimate. But if I would replace this by the true value, so the true value being v pi, so that's the true value of that state, then the whole thing, so this whole thing should be an unbiased estimate of the value that I'm trying to estimate. So that's sort of the rule of thumb to see if something is a valid update target. So just to illustrate that a little bit further, if I take the value of a state, let's just do this. So the value, the true value of the state S, the way it is defined is it's the expectation of the return received after that state. So it's the expectation of this plus 2 plus, you know, so this is the definition. Now I could write this as follows. I can break this up as follows. Yeah, I could, for example, take the first two. and then it gets let's see, can I move this? There is, wait, I'm just gonna draw a new page real quick because I'm at the bottom of my page. So yeah, so so this is the full definition, and I can sort of rewrite this as follows. So take the gamma squared, because it's a constant. I'm going to take that out of the expectation, but then I get this. So, and this whole part is just V S T plus 2. So this sort of, so gamma squared. So this shows that I can just take RT plus 1. I can take a unbiased sample by taking sort of the two-step update target. So this shows that the two-step update target, if I replace sort of my estimate by the true value, I can show that I get my that's an unbiased estimate of my original value that I was trying to estimate. So that's sort of a way to see, okay, you know, some update targets are valid and some are not. Now, if you sort of use that same technique, you can also show that another valid update target would be if you combine if you take a weighted average of multiple update targets. So you could, for example, define a new update target and say, okay, well, I want it to be 0.3 of a two-step update target plus 0.4 of a five-step update target plus 0.3 of a 10-step update target. And that's a valid update target as well, in the sense that, you know, it will give you this contraction property. Okay, so now the Lambda-return is a particular form of a weighted average over a multi-step update target. In particular, it's a summation over all the update targets. So it's a summation over all the update targets. So t plus n equals 1 to infinity. So that is, it sums over all of them. On top of that, it decays the weight it gives to each update target, decays it with lambda. So each subsequent n-step update target gets a weight of that is lambda less. So, and the last property is that, so there is some constant C here, that if you, it's a weighted average. So if you add all the weights together, it should sum to 1. So in other words, C, this should be equal to 1. And so we can now compute what C is through the geometric series formula, which, let me write that down here, in case you don't know, it's this formula. It's R to the n, where n equals 0 to infinity. If you have, this is a geometric series, and it's an infinite sum that converges to a finite value, which is a divided by 1 minus r. So if we apply that to our formula here, so you recognize the infinite horizon here as well, like the infinite sum as well. So we can rewrite this as, let's see. So C this is C divided by 1 minus lambda equals 1, which tells you that C equals 1 minus lambda. So that's the value of Z. So, you know, now we have our full formula for GT lambda, which is as follows: 1 minus lambda. So now you may wonder what happens when I reach terminal state, because, you know, this is an infinite sum. So in a continuing problem, like I can never, at no point can I sort of compute this, like, because at every time step there is sort of you know, more time step that come after it. So, but for for an episodic problem, you can actually compute it, and so we can let's compute that one as well. So, because for an episodic problem, you know that the n-step return. So, if you have an episodic problem, and that let's say the episode ends at capital T time, so it ends at time t, then you know there are no rewards that come after that. So in that case, first of all, the n-step return that ends at the terminal state is equal to sort of the full return, but it's the same is true for all n-step returns that come after that. So for n larger or equal than t, like all those are equal to the full return. So okay, let's write it down one more time. So I can break, so we have an infinite sum. I can get, because all my n-step returns that for n equal or larger than t, capital T, they are equal to the full return. So I can rewrite this as follows. So I split my infinite sum into two series. One is until the time step before I reach the terminal state. So I have this one. And one series with everything that comes after, which is t minus t to infinity. And like I said, I can now replace all those n-step returns just with the full return. So now we just need to rewrite this part over here. And we can again do that with the geometric series formula. So I can rewrite this as follows. Wait. Okay, I can rewrite this as follows. 1 minus lambda. So I want to get this one. So I subtract t minus capital T minus t from my iterator here, which means I have to add it over here, plus t minus t gt. I can now sort of take a multiplier out, so I can rewrite this as follows. Let's see, t minus 1. And gt. And this one is, as we know from our geometric series, is 1 minus lambda. 1 divided by 1 minus lambda. So I can cross these out and I just get, this is my value here. So this whole thing over here is just lambda t minus 1. So now I have sort of a my infinite sequence of n-step returns is now a finite sequence plus a certain constant times the full return. Okay, so that's the Lambda-return, and I can now make an algorithm. I'm just going to write it down in the tabular case, so I can write down an algorithm, TT algorithm, which is as follows. So I'm just going to update it with the Lambda-return that I just defined, and now I have sort of an update formula. I have an algorithm. I can make this into an algorithm, and that's my Lambda-return algorithm. And this is the Lambda-return algorithm for prediction. Rhythm for prediction. Now, the one thing about this algorithm is that I can only compute my Lambda-return at the end of an episode. So I can't do it. During the episode, there is no update securing. I have to wait until the end of the episode because only at that point I can compute my Lambda-return. So it's an offline algorithm. Okay, I'm just gonna pause for a moment to take questions, and I have to look at the time as well. Like, what's the typical? It's 50 minutes, right, for the?
Well, we usually stop at 10:20, but we can stop at 10:15 after a couple of questions, and then continue at 10:30.
Yeah, let's. Well, I can go to 10:20, but let's take some questions first. Okay. We'll stop in a few minutes.
Okay, so questions from the class. I think people in the Zoom, either you can type your questions or ask them directly.
So if there is no questions, I can sort of move on to the eligibility traces.
Okay, so there's a question in the chat. So can you just go over how you removed the sum in the previous slide?
Just see. That was it. Was that this one, or was that?
No, I think, how did you remove the sum in the finite episode case, like in the episodic setting?
So okay, so how I removed it over here? Okay, yeah, previous slide. Okay. So.
Excuse me?
Yeah?
Yeah, it's not this slide. It was like the one where you replace the iterator with t minus big T, capital T minus t minus 1.
Right,
so
right.
The finite horizon slide, like, did we miss that? I'm not sure if Zoom allows you to keep the slides like that.
Well, I have a couple of white whiteboard. I'm not sure I still have that, but I can quickly. So at some point, like I had an infinite sum. I broke it into two parts. So 1 going to t minus 1 plus t n is t minus t infinity, and this was this one, right? And how do I remove this one over here? That's the question?
Yeah, the second term, please.
Okay, yeah, good question. So let me write down the geometric series formula one time. So this is what we're going to make use of. This is a divided by 1 r.
Okay, yeah, I got it now. I can
Oh, you
see
got it? Okay.
that.
Yeah, great.
So the entire sum of lambda to the n minus 1 is equal to the result of the geometric series, and then you choose the 1 minus lambda.
Yeah, so you have to make this equal to 0 first, right? There's 0 over here.
Yeah,
So,
exactly.
so that's what you do first, and you can do this by subtracting from the iterator t minus t. So if you do that, you have to add plus t minus 1 over here just to account. So you can take this, and then you're sort of making use. You can split this up just like this 3 plus 2 is equal, simple rule. Right? This is equal to this. So you're applying a similar rule over here, where you're now writing this as 1 minus lambda, taking it out of it, t minus t1. And now so you rewrite it like this, and now the geometric series formula add in, and this is 1 minus lambda. Okay. Before we go to the break, I will briefly talk about eligibility traces as well. So let me do that as well, because eligibility traces, what is it exactly? So we write down the formula for the tabular case again, because it's just easier to see what it is. So, and I'm going to use the notation they use in the book. So I use a Z. But typically,
I'm sorry, can I interrupt you for a second?
Yeah.
It would be possible to mute the other Sarath Chandar. Thank you.
Yeah, great. Thanks for that. Yeah. So this is an eligibility trace. Sorry, gamma lambda z t minus 1 s, for if s is not equal to st, or it's gamma lambda z t s plus 1 if s equals to st. Okay, so this pretty much tells you everything you need to know about the eligibility trace. At least it tells you a lot. So it's a decaying trace. When you visit a state, it gets a bump in value. And at all the time steps you don't visit the states, its value decays with gamma lambda. So, and you maintain this trace for all states, all states from your state space. So what the eligibility trace, it keeps track in a way how recently you visited a state. And so the update target then, if I sort of draw first without, if you don't use eligibility traces, like the normal update is like this, VT S, and I'm going to draw it in a way well, let's draw it like this. So this is the update you know, plus alpha, and plus gamma. This is if S equals ST. And there is sort of a trivial update that people don't write, but it just means like all the other states that are not the current state are not sort of the trivial update happens. So that value stays the same. Now, if I use, oh, sorry, this should be +1. So if I use eligibility traces, it's slightly different. The update rule is like this. I'm gonna use this plus alpha ZTS plus well, RT plus 1 plus gamma VTST plus 1 minus VTST. Oh, and there should be also a minus VTST over there. Sorry. So there's two differences. So whereas with regular updates, you're only effectively updating ST. With eligibility traces, you're updating all the states relative proportional to the value of your eligibility trace, which means that this TD difference, like for recently, all the recently visited states get a fairly substantial update, and the longer it has been that you visited a state, the smaller this trace value will be, and the smaller the update. So it's a very different way of doing updates, and it's sort of it's very strange to think about it, like, because this one was sort of, it's based on stochastic gradient descent. If you can very easily derive this update rule, and it makes a lot of sense. It's, you know, it's just like from the fundamentals, it's just based on stochastic gradient descent. This is a very weird one. Like, it doesn't, it's hard to explain why this would work, why this is a good idea, that, you know, you update recently visited states. And it seems very weird, and to deviate from sort of all the theory around one-step updates. But it's actually, the reason it works is that it's just a algorithmic trick to do a multi-step updates, and you can sort of write it out as a multi-step updates, and that's sort of the relation between sort of the Lambda-return, the Lambda-return algorithm that is showed, and this eligibility traces update. And I'm gonna dive a little bit more deeper into that relation in the second half. So we're gonna take a break now for, I think, 10 minutes, like Sarath.
Yeah, so we will continue at 10:30.
Yeah, and I'm sort of in the second half, I'm gonna switch to my slides, because this is also where I did my research of trying to find exactly what is this relation between sort of the Lambda-return algorithm on the one hand and the eligibility traces on the other hand. And some things were not completely correct, and so that's where I made an improvement there. So after the break, I'm gonna, it's gonna be less writing, more slides, and I'm gonna sort of dive deeper into the relation between eligibility traces and the multi-step update targets.
Okay, so we will resume at 10:35.
Yeah, if people have questions during the break, feel free to put them in the chat, and I'm happy to answer those.